This video is about conduction. Hopefully you've had experience of holding a metal spoon over a flame or stirring a cup of hot bowl of soup or a cup of soup, and you'll notice that one end will get a lot warmer. So in this particular case, the heat from the flame causes the atoms and the free electrons in the end of the metal to move faster, and these atoms start to jostle around against each other, and then they start to pass on that energy from one end to the other end. Here's a great animation I just found that shows the conduction of heat. So I'm just going to press play here, and you can see that the heat over on this side is being slowly transferred from this end over to this end. And these molecules are jostling around and passing along the kinetic energy from one molecule all the way over to the other end. And eventually the right side of this metal will become very hot. So what is conduction? Well, conduction is that heat that is transferred in a material between the collisions between the adjacent atoms and molecules. All right, so what they're doing is they're transferring that average kinetic energy. It always flows again from hot to cold temperatures. Conduction occurs between materials, or essentially it occurs from solid to solid. It's a heat flow rate that occurs only in solids. So if you consider some slab of material with a cross-sectional area A and a difference in temperatures, this is the hot side, we'll label that as TH, and then over here is the cold side, we'll label that as T sub C. So therefore, these two temperatures have a temperature difference, which we call delta T, and then we have the cross-sectional area we mentioned, and then this delta L represents the thickness. That's the difference in the size from one side to the other side. So the rate of heat flowing through this material depends on the cross-sectional area, the spacing between the layers, and of course the temperature difference. And one other factor, the thermal conductivity K. So that thermal conductivity changes from source to source. If you look down lower in your notes, you'll see that there's a list of thermal conductivities right over here. And you can see that most metals here have very high thermal conductivities like aluminum and steel. Stainless steel, by the way, is not the same as steel. Stainless steel has a very low thermal conductivity. So that depends on the metal itself, how free those electrons are. If you have a lot of free electrons, then that also helps transfer that average kinetic energy from one atom to another atom. So hopefully you'll notice that if you look up here conceptually, if you were to take a particular layer and you have two layers and you double the length of that layer, the distance between them, then sort of like if you think of you have a house and you were to increase the thickness of your walls, well, that's obviously going to decrease the heat flow because the thickness of the walls is inversely proportional to the heat flow rate. Of course, if you increase the cross-sectional area, like you have lots of windows in your house, and then increasing the area will also increase the heat flow rate. And lastly, the temperature difference between the two layers increases directly with the heat flow rate. Going back down to our list here, we can see that these materials that have very high thermal conductivities are what we call good heat conductors. Those with low thermal conductors or low thermal conductivities will essentially be called insulators. So things like, goose down, wool, they have low thermal conductivities and called insulators, and you've got most metals over here that are good conductors. And down here in your notes, I've listed a bunch of key problem-solving steps. So the first thing you want to do when you solve a problem is to draw a picture and identify the direction of the heat flow rate. So if you take a look at example 1, you'll see that I've drawn a picture over here, and you can see the heat flow rate would go from hot to cold. And then you label all the sort of given things like the cross-sectional area, the thickness, and the difference in the temperature. So make sure you have all the important information. You may have to look up thermal conductivity if it's a problem in your notes or something like that, or a WebAssign. But if you're on a test, we're going to give you these thermal conductivities. Okay, second thing is, this is a little bit trickier, is what happens when you have layers that are in succession with each other. I call that in series with one another. So these two layers would be in series. So let's suppose that you have a thermal conductivity Ka here, and then you had another material K sub B. So how do you solve a problem where you have two different layers? You might have a layer of like insulation here and then a layer of bricks or something like that. So how do you solve that kind of problem? You have a temperature here and a temperature here, and then you have this intermediate temperature in between, we might call that the T, the interface temperature. So you'll see this example if you look in your notes on example number 2, we have steel and copper. So the key in solving this problem when you look at it is that the rate at which the heat flows through the steel and through the copper are the same. So the heat flow rate through steel and the heat flow rate through copper are identical. And that's under the assumption that these two layers are in steady state with each other. What I mean by steady state is that if I were to measure the temperature all the way through here, they would all be identical temperatures. And so the rate at which this heat flow is going through here is exactly the same as what it is on the other side. And you can make that assumption because it's kind of like what you did in electricity, where you would say that one resistor is, say, in series with another resistor, R1 and R2. We could say that the current through this resistor and the current through that resistor are equal to each other. So think of like heat current like electrical current. So the amount of charge that flows through here per unit time is the same amount of charge that flows through here. So this is kind of conservation of charge, but in this case it's a little bit different. It's conservation of heat flow. Going back to what I wrote in the notes earlier here, so what you want to do is label a temperature T that's in between the two layers, and then you'll see that when you solve example number 2, how we would go through that. The second or third case here is what you do when you have two layers that are in parallel with each other, like this picture over here. So maybe you have K1 here and K2. These are now have two different pathways to go from here to here. And so to solve this problem, you'll have two heat flow rates. You'll have one from this layer and one from that layer, and really the heat flow rate for this whole system would be the sum of these two heat flows. Where here, these two heat flow rates are identical, equal to each other, and it has a net heat flow rate. So the net heat flow rate through this whole section here, we'll call that H, would be the same thing as H through A and the same thing as H through B. But over here, the total heat flow rate would actually be the heat flow rate through 1 and the heat flow rate through 2, added up together. So this is what we'd call a parallel situation, where the layers are in parallel. You may remember what you did with circuits, electrical circuits, very, very, very similar. These are like two resistors in series, and these are two resistors in parallel. And so you can make some analogies between the two situations. So to quickly summarize, conduction is basically the heat flow rate, the mode that heat can transfer in solids. And it occurs because there are collisions between the adjacent atoms or molecules within the metal, and simply the energy gets transferred all the way through that material. Conceptually, I should point out, if you ever walked into a room and you put one foot on the tile and one foot on, say, carpet, and you know that both the carpet and the tiles are at the same temperature, but when you're standing on it with bare feet, you're going to notice that even though they have the same temperature, you're going to feel that the carpet feels warmer than the actual tiles. And that's the reason for that has to deal with the conductivity of tile versus carpet. The tiles can easily conduct that heat away or towards it, and so therefore when your foot touches it, it feels cooler to touch because of the rate of heat flow is much higher than it is for, say, carpet. For the carpet. Carpet's a good insulator. So sometimes it's misleading when you touch two objects, like, say, the metal on your desk and then maybe a plastic on the same desk, and they're both at the same temperature. They don't feel like they're the same temperature, even though they are. And the reason for that has to do with the thermal conductivity of the two materials. So the main difference between a conductor and an insulator is that a conductor moves the heat more quickly, whereas an insulator doesn't move the heat as quickly. It moves it much slower. And so when your foot is on that tile, the heat is being removed away from your foot at a much quicker rate to the tile, and that's why it feels, say, cooler to touch.